Hey guys, welcome to Intellipaat. In today's session, we are going to learn all the fundamentals of one of the most interesting topic in artificial intelligence, that is neural networks. Neural networks are algorithms inspired by the biological neural network that is the human brain. Now before we start, do subscribe to Intellipaat's YouTube channel so that you never miss out on any of our upcoming videos. Now let's look at the agenda for today's class. At first, we'll start with a proper introduction to neural networks. After that, we will learn what is the activation function. And then we will learn about feed-forward neural networks. You will also learn about multi-layer perceptrons. Also guys, if you are interested in becoming a certified AI professional, then do check out the artificial intelligence course offered by Intellipaat. You can find the course link below in the description box. Now without any further delay, let's get started.
So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations and then use the output to solve the problem. Now as I've already said, these artificial neural networks are based on something known as a biological neural network. So our biological neural network has dendrites, cell body and axon. So dendrites are where the input is taken, cell body is where the processing is done and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat and the labels would be either cat or not cat. After that, we give in a new image of a cat and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these three main components. So we have the dendrite, the cell body and the axon. These dendrites receive the signals and the cell body processes these signals. And the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bytes that are randomly selected. So here we have W1, W2, W3 going on till Wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail.
Just a quick info guys, if you want to become a certified AI professional, then check out the Artificial Intelligence course offered by Intellipaat. You can find the link in the description box below. Now let's get back to the session.
So here we have 3 arrows which correspond to the 3 inputs coming into the network. Now for these 3 inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the 3 inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to the sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have 2 inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have 2 different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these 2 classes. So is that really possible? Can we draw a linear line which can segregate these 2 classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is, when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between -1 and 1. So one advantage of tanh function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here, after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function, which would give us a non-linear output. So this process until here is known as feed forwarding. Now, if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network.
Just a quick info, guys. If you want to become a certified AI professional, then check out the Artificial Intelligence course offered by Intellipaat. You can find the link in the description box below. Now let's get back to the session.
Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So today we'll cover just that. So let's start with TensorFlow. So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is, model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4J. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4J is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4J is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, And then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly I'll also create a floating type constant and I'll store this in con2. So I'll type TF dot constant. And the floating value would be 3.14. Now after this I'll create a string type constant. So again this would be TF dot constant, and the string which I'd be giving would be this is Spada. And finally we have a boolean type constant, and I'll store this in con4. So this will be TF dot constant, and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values: con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now we have not started our session. So let's go ahead and start a session first. So I'll type ses equals tf dot session and I'll hit run. Now I will run all of these inside this session. So I will type ses dot run and let me go ahead and run all of these: con1, con2, con3 and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol and then I'll take in the next constant, and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol, and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type sys dot run and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions.
Just a quick info, guys. If you want to become a certified AI professional, then check out the Artificial Intelligence course offered by Intellipaat. You can find the link in the description box below. Now let's get back to the session.
So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant, and inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4, and 5, and I will add this list with the next constant. And this time, the second constant has the values of 5, 4, 3, 2, and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant, and this will have values, let's say the same values, 1, 2, 3, 4, and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2, and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is a result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be TensorFlow. Right. Now I will run this and let me execute this inside a session. So sys dot run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow. Right, so that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax, and inside that we just give the data type of the variable which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A, and tf dot placeholder, and this would be of integer type, so tf.int32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So sys dot run, and I want to see the result of b. So I'll put in b over here. Now, since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right? So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now, similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4, and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8, and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name. And let's say the value of the string is I am. Alright. Now let me run this and I'll execute this inside a session. Sys dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since there's a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys dot run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1, and we can create a variable like this, tf.variable. So guys, you need to keep in mind that this v over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20, and this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So sys.run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable, sys.run var1. Right. So we have the result of var1, which is 20. Now, since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1, and the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update, and the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run. Right now, let me run this inside a session. Sys.run, and I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. wx plus b, where w and b would be variables and x would be a placeholder. Right. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf.variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf.int32. Now, similarly, I will also assign the value for b. So b is also a variable, and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf.placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf.int32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals df dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So let's go back in 1980s. There was this crazy guy called Geoffrey Hilton. He proposed that we could mimic somehow the mind, how a human mind works, and we can mimic the way it works, so that we can also try to make a thing out of it, so that whatever our mind is doing artificially, we can also do that thing. So he proposed a paper, and everybody said that, Hilton, listen, you are doing something wrong. This is not what is right. And everybody, didn't like uh, the way things were going on. But after 20 years, almost in late 90s, around 1999, he again came up with this paper. He brought in his paper, but this time with a proof, and he won a contest that is called ImageNet in 2004. This time he came back, and everybody had to listen. So we were at 2004 when he won the ImageNet. I have two people who I've already told that ImageNet is ImageNet is actually in a competition. It is held by uh, joint vision of Stanford plus Princeton University. These guys come up, and they downloaded a corpus of images. Now they have a very large collection of images, around 1 million images, around covering 1,000 categories. They have. You can just click on explore, and you can see this tree around here. So what you have to do is that you have to make a model out of it, so that you can classify the images. So people used to make hand coded classifiers, and they were working, but at some stage they had to fail, because now let's say that fish, you are trying to detect a fish, but fish cannot everywhere be in the same manner in which you are building the hard coded thing, right? Or let's say that you are trying to detect a cat, and then you say, okay, top right if it is a eye, top left it is a eye, and then it's a squishing mouth, then it's a cat, right? But now the cat face will not always be available to you in that particular fashion, right? It might be a top view, a side view, a bottom view, any view might come up, and at that time people used to fail. But in 2014 2004, when Geoffrey Hilton came with his paper, the competition he won was with 94% accuracy, and that was never achieved, and it surpassed the human accuracy also. So that was where, when people started listening to him and he came out, then he proposed slowly that, okay, that this is what I think, that artificial neural network is nothing, but that we are trying to mimic what is happening in our own mind, right? So if I say that, what is the theory, what Geoffrey said about neural network, is that he said that artificial neural network is a computational model that is inspired by the way biological neural networks in our brain human information possesses, right? So I mean, most of you know this thing, that that our nervous system is made up of axons and okay, I'll show you the photo. that it is made up of axons and brains. I show you the photo and you might be able to. See, this is actually how a human nervous system is. Most basic diagram, and everybody of you might have seen this. So how this works is that there is a exact replicate copy of this. If I copy this, and you can attach it back here again. So these are the axon terminals that are connected to dendrites again, and this is how it flows. So let's imagine that your fingertips where you can have your dendrites, and these are like small particles again of your pure neuron connected to your brain. So this is how there are like millions of these connected, and they're connected. If I take this, okay, one more feature of Jupyter Notebook that you already know, that you can add a markdown language. So what I do is I do escape M and then I'll write HTML inside it. So I write img src is equal to, right? This is how you can write your, in this you can add that this is, right? Let's now look at it one by one, slowly. Okay, so these are called dendrites. These dendrites are the one who are like septicles. These are the one who are responsible for catching all the information and sending it forward to the nucleus. Now nucleus processes this thing and it sends to this axons and again throws it out to the axon terminals. Now imagine again that this is this copy, this is again replicated here, back here. So you can imagine that these dendrites are connected to these axons, right? And then they're flowing. Now imagine, let's say that you touched a very small, a very hot glass, right? The moment you touch the hot glass, the dendrites at your fingertips, they sense that something is very hot there. So they send this information to your brain, okay, that this is hot. Now imagine this dendrite is processing the information, sending it to terminal to dendrite, then dendrite to terminal. It goes on until it goes to your brain. Now the brain says that this is very hot. You should remove your hand. Okay. Now this process is again flowing back to the dendrite, the original dendrite here. Let's say that this is the original dendrite here. Okay, and your brain will say that this is really hot. You should remove the fingertips from the glass. And now when I'm saying that this information is going on, believe me, from your fingertip to your brain, there are like millions of these dendrites who are connecting and flowing this information. Now again, a process of reversal information flow is going on, and this time your brain is sending a signal that remove your hand from the glass, and this is again going back to the fingertip, and then you release your hand from the glass. But in real life, when you touch the glass and when you remove it, how much time do you take to remove this? It's just some nanoseconds, right? I mean, less than. Your reflexes are very strong. You just remove the hand out. But imagine what is happening when you do this. Your brain is not, your hand is not taking the decision of removing that. You might think that, okay, my hand is taking the decision to remove that. No, the hand is like a slave of brain. So every body part of ours is like a slave of a brain, right? Whatever we are doing, it is sent by the brain. The information is sent by the brain, and then it's doing. This is how your body works, right? So it's a slave of your brain, and the brain sends the information, remove or attack, whatever it is, then it reacts. But it's really fast, right? Similarly to this way only, Joffrey said that, okay, this neural network, this is how even I will also build a neural net. Now I'll show you how a basic neuron looks like. Here it is. This is the image. You write it. Basic neural. It's not a network, it's just a neuron. But this is an artificial neuron. So Joffrey said that, okay, this is how also This is how I propose. Let's do the following. Let's say that your hand is not doing anything. Your dendrites or your nervous system is not, this basic neuron is not doing anything. Imagine that it's doing nothing. But it is reciprocating the information. But how it is reciprocating the information? By activating itself. So when you touch a hot glass or something, it activates itself and then only it's transmitting the thing, right? Now imagine if this would have not activated, it would have sent nothing, right? So this is also playing a very crucial role. See, brain is sitting somewhere like a million neurons far, right? He doesn't know what is happening to your hand until and unless this neuron is sending the information. So what information will the brain process if it doesn't have the information? So these guys are very much responsible for sending the information, and they send the information only when they're activated. So this dendroid will become, this nucleus will become activated, then only it will send the further information. And see, there is also a basic kind of a information processing is going on. It doesn't mean that these dendrites are just sending blank signals. See, I'll tell you more depth inside. See, these dendrites, they collect the information. These dendrites, they collect the information and they send it to the nucleus. Now, nucleus thinks that should I process this and send it forward, yes or no, depending on that, nucleus send it further. Right. Now, how is nucleus sending is, nucleus has a particular threshold value. After processing it, it says, okay, if I am activated by that processed value, it will send it further. If not, it will keep it to itself. So this is also how a basic artificial neuron, when I say artificial, it means that the one that we are building right now in deep learning, right? This is also built. Now, what is happening is that imagine this round thing that you're seeing is the nucleus. This thing is a nucleus. But this is a nucleus, right? And these are the dendrites to it. This one, this X1 and X2. This is the way of thinking how we are intimating, and this is the tail, axon tail, and it is again connected to again a neural network. So it's a chain of multiple neurons going on. Now, if we go mathematically, what is happening inside this? It is nothing but a linear combination of all the inputs with a bias. I just went to the very human biological way and I just send a sentence. It's doing nothing. What it's doing is that it collects the input. Let's say that you have two inputs. Let's say that you have two inputs, x1 and x2. These are your two inputs. Now to every input, you will give some weightage to it. Let's say our weightage is here. This weightage is called W1 for x1 and W2 for x2. Correct? Now what I said, it is trying to build a linear regression, right? So what it does, it multiplies the weight of the corresponding input to itself. So W1 x1 plus W2 x2 plus it adds a bias to it. Now you will ask what is a bias? I'll say imagine that there is another input called x0. There is another input called x0 and the value of x0 is equal to 1. The value of x0 is equal to 1 and there is this weight associated to it that is called w0, right? So this bias is added to it and then you add this. That's it. You plus all these values, multiply plus all these values and you give this output to something called y. This is all a neuron does. Make sense? Any questions? Please ask. It's very important that you build the intuition that what is happening here. So this is the most basic, it's the smallest part of a neural network that you can pick. And the smallest part of a neural network is doing this. That it takes all the inputs that are coming to itself, give them some weightage, multiply the weightage to the corresponding input, and then sum all these, and then add a small bias to it also. That's it. Over. How is this weightage and bias being introduced? That who is okay, x1 and x0, x2 and x1, I can say okay, someone is giving to us the input that what is the temperature of the glass. Let's say it is coming from the outside environment. X1 and x2 is coming outside, but who is giving this w1 and w2? So okay, so the answer is that in a artificial neural network environment, at the very first instance, they are randomly allocated to it. So see, you all guys have learned ML, right? So how does ML work? ML says that I know the output and depending on the output, I have to give some weightage to these inputs. so that they can give me the output. Now you know that the output will be y. You know that the output is going to be y, right? Now you want to make some equation where y is equal to x1 plus x2. Okay, and now this is not the correct answer, right? X1 and x2 will never give you y1. So what you do, you add some w1 here, some random w1, and then here random w2. What it will do, it will not give you the answer. W1 and W2 will not give you the answer. You will do some corrections again in W1, W2, and ultimately it will give you Y. So this is what is happening. At the very first instance, you will take W1 and W2 as random. First is that does the process is reverse? Yes, it also reverses itself. The model will not only go from x1 from x1 x2 to y, but it can also come back from y to x1 x2. And second, let's say that he's asking Shivam, does it process recursively? Recursively, just imagine that there are like thousands of, now I'll draw it again to show you. This is just a very basic one, right? Now imagine what is going on here is that this is the small that you saw, right? X1 x2, and it is giving some y. Now here it is again, there is a x1 x2, and then this is giving me y. Now this y and y1 will become an input for some other cell, and then it is giving here. So are you imagining how will it look like? This becomes this, and this will become again an input for some other. So these are like connected, these are like throwing information from one to another, one to another, one to another, right? But this is how it works. This is how a small network looks like. And this is if I write down the theory, it says that the basic unit of computation in a neural network is a neuron, or often called as a node, right? And came write it very right. This is called a node, or you can say it a unit also. So it receives input from some other node, from an external sources or external source, that I was saying right also, right? The x1 and x2 might be an input from another neuron, or it might be given to you directly from the external environment, right? Computes the object. Each input has an associated weight to it, which is assigned on the basis of its relative importance to other. The node applies a function f to the weighted sum of this input, right?
So we'll be having the students' data, so whatever the marks based upon their marks, so we have to decide the grade. So we have to adjust whether the student is passed out or failed. So we will be adjusting the marks based upon the grade.
This is a very hard-coded problem, I think. But let me take an example that you're working on a machine learning problem where you are trying to find out the loan defaults, right? That in bank you have multiple people who take the loan. Now the bank wants to know how will this person repay the loan or not, right? Now you already have a historical data with you. The bank will give the data to you. Okay, let's say that this is the data with you. So in that data, you already know that if this is the feature of a person, this is the credit history of the person. Based on that, they will also give you that, okay, he paid, he didn't paid, he paid, didn't paid, right? And based on that, you adjust your model, right? So there also you have a x and y with you. You will have your x and y with you at that particular instance also. Okay, so everybody gets this this function thing, right? That's how this function is working. This function f is called the affine. So the f function that you see, this is called the affine thing, and it's doing nothing, right? You saw that it's doing a linear thing here. We're just multiplying the weights to the corresponding x1 x2, and you might now consider x1 x2 as the importance feature. So the more important x1 is, the more higher the value of w1 will be, right? The more lower the value of w2 is, it means it doesn't make much sense to y. So everything that we will now talk will be with respect to y. So the x2 is not making much sense to y, so the value of w2 will be very less. Let's say y is dependent on x1, so this value of w1 will go more higher, right? And then your bias you already have, this is a static thing, right? Because the x naught associated to it is equal to 1, right? Let's now go back at what further happens here. Now you get the y out of here, right? Now this y thing is a little, you have got the answer, and this might be greater than 1 or less than 1 also, right? So there is no measure of this answer. It might happen that w1 w2 is very small. Let's say w1 w2 are very small, then the value of y might be almost equal to 0, right? Or let's say that w1 value is very high, like very high, so the value of y might also get very high, right? So now this might bring some bias, this might bring some ambiguity to our model. This y might be sometimes, next to infinite, it might be equal to infinite, or it might also be equal to 0, right, depending on the variables. And we don't want that. We want our y to be in some particular range, right? We want our y to be in some bonded weights, right? Then comes next guys whose names are activation functions. Activation functions. Now we got to know that how this y is made, right? How this y is ultimately achieved. Now to adjust the value or squeeze the value of y, we need some other thing, right? We need something that can control the value of y, and these are called activation functions. Now what activation functions does is that they will take the value of y and they will squeeze the value of y in some certain range. What they will do, they will squeeze the value of y in some certain range. So we have multiple, let's say we have a step function, we have a 10h function.
Shivam, Sanjay this side. Can you please come again about this activation function? Not getting you properly.
So let's come back what this activation function is. So you understand that the value of y, how it is calculated, right? It is now totally dependent on w1 and w2. If the value of w1 and w2 is very less, I mean 0.0000, or let's say 10 to the power minus 23, then the y is going to be very less, right, next to 0. Or let's say that the value of w1 and w2 is like 10 to the power positive 48 plus 48. So this might be very high. The value of y might be very high. There might be no standard to control this value of y, right? Mathematically, there is no, this value can go from negative infinite to positive infinite, right? And this is not a very good range to get about a particular output, right? So what we do is we introduce something that is called activation functions. Now what this activation function will do is activation function will make sure that your output that you have got y should be in some particular range. What it should be? It should be in some particular range. Now how do you decide that who is going to be in what range, and how is that range called? See, the activation function, if I ask you mathematically, the mathematical purpose of introducing an activation function is to squeeze the value of y between some variable called 0 to 1, right? Majority times. So the purpose of activation function is to bound the y in some range, right? And this range might be minus 1, say 1, 0 to 1, or sometimes 0 to infinite. It might be different things, right? I was at this thing that mathematically the value is to be squeezed between 0 to 1. But if I talk to you about statistically why I am doing this is, now imagine till here, till this particular range, your model is a linear model. Everybody agrees with me, right? This is a linear model. Nothing non-linear have been done till now, right? All the things that we have done till this step in this circle, everything is linear. There is no non-linear thing, right? Now, linear things are a little bad at classifying things if there are more than 3 classes, right? If I ask you, if let's say there are 3 classes, one is like crosses, right? One is circles, right? And one is some triangles. Now, can you make a single line and can divide these 3 data? No, right? If it would have been two classes, you might have drawn a single line and you might have divided the data into like two classes, right? But if it is a three class data, how will you divide this? You have to ultimately make a triangle kind of a shape or this kind of a shape, right? Then only you can divide the divide this thing, right? So I'll show you a photo also. Let's say, let me give you an example, then I'll show you how this works. Okay, can any one of you, let me hide it here. Now this is this thing in front of you. Everybody can see your data. There is this red dots and there is a blue triangle in the screen, right? Everybody can see this. Now can you make a linear model that can separate these two things? This can only do in a two dimension, right? But if I say you that, okay, see a magic, anybody wants to try this thing? How will you do? No? Okay. What I'll do is I'll remove this now. So what I did was I introduced a third dimension, and now I could easily separate by introducing a hyperplane here, and then I can say, okay, something that is above this hyperplane is red, something that is below this hyperplane is blue. Makes sense to everyone, right? So this is why we do activation function, to make sure that we want to classify things more better, to make things more clear. We do an activation function. So mathematically, why we are doing activation function? Because we want to squeeze the value of y somewhere. But if I talk statistically, what we are doing, we are introducing non-linearity in a linear model, because linear models are very much not capable of classifying things in when the number of classes increases. So now we saw that as soon as we increase the linearity, if we increase the dimension in the data, if we introduce non-linearity in the data, what it is doing? It increases the chances of making a linear separable model, right? Right. So if I say in three times, first mathematically squeezing the y. Second, if I say graphical thing, why we are doing this? Because we want to introduce a new dimension. And statistically saying why we are doing this, because we want to introduce non-linearity inside it. Now you might be asking what these functions do. It's a very good question. I have activation functions graphs. See, this is how a sigmoid looks like, a tanh looks like, a ReLU looks like. And see, everybody is bounding. So see, sigmoid is bounding between 0 to 1. Tanh is bounding between -1 say 1. ReLU is bounding from 0 to infinite. So it lets go everything that is going above. Yes, we have step function also. Step function says that you can go, if something can be only have two things, either 0 or 1. If something is negative, it goes 0. If something is positive, it goes 1. It's a step function, sigmoid, tanh, ReLU. So there are multiple things. These are doing the same thing that we want to do for a activation function. ReLU, you can understand that if something is negative, it says it's a 0. And if something is positive, it lets go whatever the value of this is, right? I write the variables in here. This is what brings in. Sigmoid is this, tanh is this, and value is this, right? What is the maximum of 0 to 1? Whatever value it will take, right? This is what activation functions is. Let's say that you have this thing called y1 and y2, right? And now the value of y1 and y2 is very large, right? So this y3 will become ultimately also very large, and this y4 will become also very large. And we know this is not the exact thing. We always expect our output to be in the form of 0 to 1 if it is a classification problem, and if it is regression problem, then it will always be in some range from 0 to 1. right? You all agree with me, right? In machine learning also, whenever you did a classification problem, you one hot encoded the problem. So you never said that the output is going to be a C80 cat or DOG dog, right? You always said that, okay, if 0 comes, this is cat, 1 comes, then it's a dog, right? You did the same thing, right? In machine learning also, or if it was a regression problem, then you always regress a value from 0 to 1 with a multiplicative factor, right? So this is what is happening here also. The y3 and y4 ka value can never go up beyond the limit. To control that limit, we have to squeeze the value. And see, when I'm saying squeezing the value, that is in mathematical format. But if you see in statistically, what we are doing is that we have to introduce non-linearity into the data, right? Because linear data are not linear equations are not good in separating non-linear data, right? Right, this becomes separable. You see, now it is very much separable just by a simple hyperplane. Okay, so coming back to a feed forward neural network. So see, this was the input x1, this was input x2, and now what a feed forward neural network expects is that a hidden node should be connected to all the inputs. What does it expect? It should be connected to all the inputs that are in the previous layer. So this is, let's say this is called layer, input layer. Wherever your hidden neurons, this is called hidden layer. And your outputs are here. This is called the output layer. Now, when you are building this feed forward neural network, your responsibility is just one, that whichever neuron you're standing, let's say we are standing on this particular neuron, let's say this neuron, this neuron. Now, the only thing that okay, this is not a neuron exactly. Oh, sorry. Let's say we are standing on this neuron. Now, the responsibility is just this, that if you go to the previous layer is the input layer, all the neurons in this layer should be connected to this hidden node, right? Similarly, output 2 also expects the same. You go to the previous layer. So this is the output layer. What is the previous layer? Hidden layer. So all the neurons in the hidden layer should be connected to the output node 2. Make sense? Or if I make it more easily, let's say that whichever neuron you are standing, just go to the previous layer, and all the neurons in that previous layer should be connected to this particular neuron, right?
What is this layer signifying here?
Correct, very good question. So what you are doing is you have stacked all your neurons one by one in some format, right? So all your input neurons, so see, whatever you made in this above statement here, in this above thing here, so this x1 and x2, this is this x1, x2. This might be x3, x4, x5, x10, right? So these x1 and x2s are what? Inputs, right? So what you do is you collect all these and you just put it inside a layer here. This becomes a hidden layer. Now you will not only have one neuron, you will have multiple neurons, right? So what is happening is that so what you have done is, rather than having just one neuron, what you have done is you have made multi-neuron system. This is a feed forward multi-neuron model here. So what you're seeing in the previous photo, that is image that I showed you, that was just a multi-input single neuron, but now you have multiple neurons. So what you do is you stack these neurons in this layer, then you can have, so this is just an example. What you can do is you can have an image like this also, multi-layer. Okay, so now if you see Tarun here, so what is happening is these are your inputs x1, x2, x3, x4, right? This is your input layer. This is your hidden layer 1, where all your affines and activations are happening, right? This is your layer 2. Again, all the affines and your activations are happening, and this is your output layer, hidden layer HL2. This is HL1, and this is input layer. So what is happening is that, let's say this is called neuron 1, that y1 just marked. So let's say this is n1, this is called neuron 1. Now what is happening is that this neuron 1 is connected to x1 also, x2 also, x3 also, and some bias also. So what is happening here? This affine will be happening here. What will be happening? It will be here as w1 x1 plus w2 x2 plus w3 x3 plus some bias b will give some output called y. And here you will be having a very small activation function also residing here, right? Similarly for this n2 also, this n2 is connected to all the inputs, right? This n2 is connected to all the inputs. This n2 is connected now. It is connected to this, to this, to this, and this. Now n2 will also do some affine and then bring some activation, small activation function here, and it will also give some output called y2. Similarly, y3 will also be here. Now this y1, y2, y3 will become input for these neurons. Let's say we call this neuron as n4. Now this n4 is connected to this, this, and this. Similarly, again affine, and let's say it gives the output called O1. Now O1 is here. Similarly, O2 is here. Now this O1, O2 is all will also become input for this. Let's say we call it O1 right here. Right, this is O1. Y4. Let me remove this. Sorry, sorry. We were here that there is this some output called Y4, and there is some output called Y5, right? Now what is happening? Y4 and Y5 will become output for this O neuron, and they will give some output O1 and O2 similarly here, and then you will have outputs, right? This is how a multi-layer neural network works.
How will we know that how many layers?
Correct. This is one of the very good questions that first of all, how many layers do you want? This is the layers that you have, L1 and L2. Now you might have another question that okay, in one layer how many neurons can I fit? So there are currently 4. I can fit 5, 6, 10 also, right? I can fit 10 neurons also. So who is going to tell me that how many neurons and how many layers? This is what exactly what data science you are going to do here. I mean, everything is built for you. This neuron thing and this all thing is this is already built for you. The only thing that you have to do is that you have to come up with the optimal number of neurons and optimal number of layers for each neural network. And now who is going to decide this? Very good question. This is you who is going to decide this. And how? Okay. So first answer is that hit and try, that everybody will tell you, and I am also telling you that the first approach is hit and try. Let's say that you are doing a very new problem. I mean, you don't have any idea, you are just doing. So one thing is that you'll go with the hit and trial model. Second is that as soon as you become a little bit expert, now you start learning, okay, this is how my model is reacting to this particular neural network layer. Then you see the model capacity. Okay, so let's say that, so see, this is a very good question, but this is also an advanced question. Now see, when this, let's say this is called neuron 1. When this neuron 1 is connected to x1, x2, x3, there is a weight called w1, w2 on this layer, and w3 here, right? So, but when this n2 is connected, this is not w1, w2, w3. There is w4, w5, w6. So when this x1 is connected to this n2 here on this line, there is another weight, that is w4. So imagine how many weights are there for 3 inputs, 3 neurons. There will be 9 weights, right? Now there are 9 weights. Now imagine here again that you have 3 inputs and 2 outputs, 3 to 6. Then you have 6. So 9 plus 6. Then again here 2 to the 4. So you will have 2 plus 4. So 9 plus 6 plus 4 is 19. So 19 weights are there, and then you will have 3 biases here, right? So 19 plus 3 is what? 22. So for the small neural network, you have 22 values that you have to predict, right? Because y1, w1, w2 we have taken as what? As random, right? And biases are also random. So you have to adjust them in a very optimal way so that you can get the output as y. So now imagine that you have 22 things that you have to train here. 22 things that you have to predict, not predict, but you have to optimize, right? And now let's say that you have a data only for like 10 rows. Now does this justify that you will have 22 things to adjust in the 10 rows of data? So this is called capacity building. So what you have to do is that you have to check your model if your model is even capable, if the data is even capable to adjust these values, right? Let's say that you are just doing a simple addition, right? If you give two numbers, your model has to give some output, right? Now let's say that you have 1,000 examples for it, but now you're building a like say 1,000 layer and 1,000 neuron per layer, 1,000 neurons, and then you have 1,000 layers. Now does the model require this much of data? No. The data will be lost in some third or fourth layer only, right? And see what I just said in just last 2 3 sentences. This will come slowly with the experience in you also. So what you'll do, so whenever a new problem comes to me, I first of all read the research paper through it. See, because we are not researchers. Let me be frank with you. We are not researchers who are going to make things. We are deep learning engineers here, right? We have to implement the engineer and we have to solve a business problem through it, right? So what you do is first of all you read some papers out of it, right? Then you get the intuition of how do you build a neural network around it. Then I do some hidden trial error. Okay, this is how you build and this some changes. And then slowly you understand, okay, when I change this thing is affected more. Then you reduce and more. Then you have some prior knowledge also like that I told you. Keep capacity, that what is the capacity of the model. Let's say that you have a very large data, but you are just building one layer. Then the data is underfitted, right? Or let's say that you have very less data, but you have made a very big neural network for this. And this is called overfitting, right? You have a very over number of neurons for your model to be predictable, right? So slowly you will you will have intuitions, and this is I will tell you, with your when you will be doing your first problem in a neural network, you will understand slowly. See, you might be thinking that I'm not taking to you practical, right? I am not telling you about any real world example, but this theory is really important. I might directly jump to the code also, but that will make no sense to you after 2 or 3 weeks, right? Because code anybody can write until unless you don't know. Okay, what will happen is the next after 2 or 3 months when you will be making your own neural network, you will fail that. Okay, which activation function to use? Then this thing will occur. Okay, so see, this is what he is talking about to all the people. This is what he is talking about. Let's say that you want to add more layers. So currently there is only 2 hidden layers. You want to add more, add more, add more, right? If you want to increase per layer, you want to increase the neuron, you might go like this also. Okay, you might like, I'll reduce it to like, let's say 6. This I'll reduce it to 4. This and 2 and this is 1, right? This is how your neural network will look like. These are the 2 inputs. Now every input is connected to the every neuron in the first hidden layer, right? Then second, then third, and fourth similarly. And this is how the data is flowing inside it. You can see now slowly. When we put every X into each neuron, does every neuron give same Y? Very good question. But no. See, Kim, if we come here, it would have been the same if they would have same W, right? So if X1 is connected to N1 here at this layer, it has W11, right? But when X1 is connected to N2 here, it has something called W12, right? So there are different weights. So it is coming from X1, but because it is connected to different neurons, different input neurons, they will have different weights also. Understandable? So to other people, what Kame is asking is that, okay, that you are doing affine. I understand that you are doing affine, but let's say that, let's go back to affine equation. Because the value of x1 and x2 is constant, the output will always be constant, right? But no, because y1 is made up of this equation, and this equation is also driven by w1 and w2, and the w1 w2 values are different, the value of y will also be different in each case, right? Makes sense, right? And when we were asking about a real world problem, this is how a neuron will work. Okay, I have this also, don't worry.
So you mentioned overfitting and underfitting neurons,
Yes,
so how do we come to know that based on the Y or
again a very good question. So I took these two words called underfitting and overfitting. This is how it actually works. This is a intuitive GIF. Okay. So what Suresh is asking is that I took two words in overfitting and underfitting, and how do we address this problem? So what we do is that we divide our data into two parts, and I think you must have also done this in ML also, right? Training data and validation data, right? Not two, just three parts, right? Training, validation, and testing, right? So what you do is whenever you are training your model, you just make a slice, another slice of a data, and this is called validation data. And you will never show this data to the model, right? So no, you are never going to train your model on this particular data. So what you're doing is you will never show this data to the model, so model will never come to know about it. So it will never learn about it also. Now once your model is made, what you will do is you will test it on this data. What you will do? You will test this on this data, and then the model will say, okay, this is how it looks like. Okay, this is what the predictions are, and then you'll see the predictions, and then you'll compare the predictions. Okay, this is not what I wanted, so the model is underfitting or overfitting. Now how will you do underfitting and overfitting? You'll do a confusion matrix, and then you'll see that if the model is just giving out you only one classes, let's say that your data had 10 classes, and if the model is just pushing towards one class, then this is overfitting. Your model is overfitted at a very lot level. Okay, then we have another question from Game. He says that it means now this dog image, when we expand this image mathematically, this will come out to be three things. One is called x1, x2, and x3, right? Now what we have to do is this x1, x2, x3 is done towards from our end. Now this x1, x2, x3 is connected to this neuron 1. Okay. Now x1 is connected to n1. This is called w11. But when it is connected to n2, it will have some another random weight called w12. W12. Make sense? So number of neurons you can increase as much as you want. As much. You can have n3, n4, n5, n6, n7. Doesn't matter. But you have to make sure that this w11 is not the same weight for all n1, n2, n3. Right? Cool. Thank you. Thank you. So inside the matrix, you can see there are multiple values. The value ranges from 0 to 255. 255 is for like utter black and 0 is for white. Right? The value ranges from 0 to 255. You can see the more black it is, the more the value it has. Right? So what is happening is that these are the multiple inputs that you will have inside your images. Multiple inputs, and all these inputs will go in here. So in this particular example, you are seeing 3, but this time you will have more. So these all the zeros in first, all the values in second, third, fourth, fifth row till the 28th row. You will have all the numbers inside this input layer stacked one by one. So ultimately you will have 28 cross 28 is equal to 784. So you will have 784 inputs normally for this small image. And this is you guys were all asking about me how this will work in real world. So real world, let's say that you have an image of 500 cross 500. So that becomes around like 25,000,000. That means 2.5 million inputs you will have for single image, right? And let's say that you have 10,000 images, so this becomes multiplied by 10,000, right? So these are the number of inputs that will go inside one by one by one by one by one. So one image will go one time, two image will go two, second time, third time, and then based on this, the output is the model is going to do some calculations in the hidden layer, and then it's going to predict the output, and it will give you some output at y. Okay, so now we'll turn up the pages and we'll move to multi-layer perceptron. But now we might have multi-layer perceptron architecture. Now a multi-layer perceptron architecture simply means that you might have multiple hidden layers. Okay, so apart from having a input layer and output layer, you might have hidden layers in between of them also. Whereas a single perceptron was only a linear function, a multi-layer perceptron will have multiple linear and non-linear functions, a combination of them, right? I'll show you this. And I was not able to continue today and tomorrow. Today also you will not be able to continue. Okay, don't worry. I'll push the notebook in there and then you can have it. Okay, so I think you already saw this, but I have a image of multi-layer perceptron also. Let me show you. Okay, so this is how a multi-layer perceptron looks like. If I just minimize my screen a little bit, so you can see this now. Again, just to memorize things up, this is x1. This is what your input. x1, x2, these are your two inputs, right? Now you have a single hidden layer right now here. You have this one neuron here. Now you already know that what is the calculation going on inside. There is the affine function. Affine function, what it does, it takes input from all the behind layer neurons, right? So if I say it takes input from all the behind layer neurons, and if this is a hidden layer h1, then it means that it will take inputs from all the neurons inside this input layer, right? So this is x1, then this is connected, this is x2, this is also connected. Now whenever a neuron is connected to another neuron, it is connected through some weightage corresponding to it, right? Let's say this is w1, this is w2, right? And then you might also have a x naught. Now the x naught is always equal to 1. So you might say this is just a bias as b. Now this b is like constant to this neuron also and to this also, right? I change this and it not will come to this. Okay, so now this is x1 and x2. For this, when they are connected to this neuron, the one that is downwards, and this neuron, they are connected again to some weightage, but this weightage might or might not be equal to the w1 that is the one that is described here. The one described here, this is never going to be equal to this one, right? So these are different weights associated with different. So you might, to make it more simplified, you might think that whenever there is a string connecting two neurons, it is connected through a weightage, and this weightage is different for each one, right? This weightage is different for each one. You might also see the equation here down here. W naught in plus 1 plus W1 x1 W2 x2. Now you know that W naught is equal to 1, so we have replaced W naught is equal to 1. Sorry, x naught is equal to 1, so we have replaced x naught with 1, and W naught in itself you can say W naught, or what people like to say is it's called as notation called B, and this is called the bias of the neural network. Okay, bias, and these W's are called the weightages, right? And then you do again a summation out here, and this time you do the final output, and then you give the output right here, right? You also remember that after every neuron there is also activation function which is sitting here, here, and here. They are also present on the outer section also. This and this, they're present here also. So they, and then you read that there are different types of activation functions. From step function to sigmoid, then to uh, softmax. We have different. I'll slowly go through each of them, and then you'll understand that how they interact, and how you might be also changing them according to your needs, right? Okay, I'll minimize it. Visible now? So now once we are done with this perceptron layer, now okay. So this is called a feed forward neural network. Just one thing, feed forward neural network. Once you come from here, this neuron, you go to here, then there some calculations goes on. Then you come to here, which is taking connections from this and this neuron, and then you give the output, right? Now let's say the output comes out to be some y1, whereas the actual output was, let's say, y, right? Now there is the error associated to it. So you say that you have an error, and what is the error? Y minus y1. This is the error, right? Y was the actual answer that should come, right? But you are saying the answer is y1. Then y minus y1 is actually the error. What it is? It is actually the error. This is actually the error, y minus y1. Now your model, you say to your model that model, you have done some kind of mistakes. Now if you go back inside your session, if you go back to your session, you might see some errors inside it, and that error might be equal to y minus y1. So go and do the changes. Now if you see our function that we have done till now, the result through which we have come till now here at this point y1, it is all how much dynamic things you have taken, I mean non-static things you have taken. See, x1 is always going to be static, right? This no one is going to change this x1 and x2 because these are given by the data itself, right? So the data can never change itself. It is you who has to change, right? And then what is the thing that we have taken assumed? These are the values of w1 and w2. W1, W2, and W naught. These are the similarly these W's here. I mean all the W's that are here, all the W's that are here. These values are something that you have assumed, right? So now what the model says? The model says that the value that you have assumed, W1 and W1, W naught, W till Wn, these values might have some kind of a correction because the current values of W are present are giving some error, that is y minus y1. So to reduce this error, you go back and check your values of W and switch the values of W to such an extent so that they minimize this error, right? Whatever I said just now statistically, right? Makes sense to everyone, right? What I just said here. Okay. Now this thing is called backpropagation. Back. Now this thing is called backpropagation. Now backpropagation, if I take the copy of thing, can we try different activation functions too? Yes, you might try whatever activation functions you want to try, but there are some. Okay, so Oman has asked this question that how do can we use different activation functions also? Yes, it depends on the problem that uh, uh, what functions do you want to choose. So I'll tell you my particular example. So I was working on this library that is called DOLD5. Here what we are trying to do is that we are trying to restore colors into uh, images that don't have color. So I mean, if you talk about images that are like from that are before 1924. So we have some German artifacts. Those are before 1924, and those are totally black and white images to us, right? So what we have to do is that we have to fill images inside it. Now filling images inside it is, I'll tell you, it's a complex process, but there is a form of images that comes out that is called the LAB images. So if someone of you who has interest in photography uh, or if you understand what images are, then you might have heard this term called LAB. LAB images to convert. Now the range of LAB images is from minus 128 to 128. So here my task. So if generally if you see the activation function, if you remember from the previous class, all our activation function from ranging something from 0 to 1 or minus 1 to plus 1, right? Now I wanted something that has to go from minus 128 till plus 128, right? And how will these things two go? So accordingly you can change your activation function and you make your own function out of it, right? Make sense?
Yeah, I forgot you in last lecture you said whenever you're trying to bound your values in a certain point, then you use
Correct,
different activation function. I just reminded.
correct, totally correct. So so this is all about the feed forward. Now feed forward, if I just say in one line, feed forward is going from input to output. Now if you want to come back from output to input to make corrections, that is called back propagation. Now back propagation is one of the most used, or I should say, okay, now visible. Okay, now this is one of the most not used, but this is one of the most obvious things in backpropagation. This is in AI, and why this is famous, because this is the main backbone for AI. This is how AI learns itself, right? So people say that AI is learning from itself. No, it's not learning from itself. It's learning from the errors. whatever error it is making, it goes back and it checks. So see, a human tendency of error checking is what? Let's say that you are doing some calculation and you do some error. What do? You go back again to the calculations and you check, okay, I did this mistake, and then you correct it, right? This is also the way how machine is also understanding. So what machine does, machine does some calculation, it calculates that there is some error, then based on the assumptions that it took, or based on the that the assumptions it took, it thinks, okay, these are the things I assumed and this is now the error. So what it does, it goes back and say, okay, I will change my assumptions, I'll tweak my assumptions, and then I'll see what is the error again. This is a iterative process. So again, let's say that in backpropagation, what will it do? It will try to change the values of W1 and W2, right? It will try to change these values of W1 and W2, and then it will again go in the forward direction, and it will again see, okay, again there will be some error, but this time the error will be less as corresponding to the previous error, right? Now again it will go back, then come forward, again go back, forward, go forward, invert, forward, backward, forward, backward. This will happen multiple times, and at one point the error will saturate. The error will look like this. The error graph will look almost like this. Here error is on the y-axis, right? And this is whatever you say, time on the number of epochs or steps, let's say, as of now. Steps means that how many times you have gone forward, backward, forward, backward. So you can easily see here that that the error was very high at this particular point, but then it slowly decreased. It decreased till here, but now it's almost saturating. So it's like almost saturating, and at one instance it will be like parallel to the x-axis. It will become parallel to your x-axis. This is how it looks, right?
Shivam, so how this program will go back and forth? Means it's APIs, or we have to manually do this every time, run the program each time, and or run the program in the reverse order? Can you make it clear?
Okay. So so the point is that first of all we'll do it on in our hands. So we'll do it manually first.
Okay.
But good news for you is that no, you don't have to do it manually. All these things are like handled by the framework itself.
Many times we have to go back and forth so that it is
No,
minimized
no,
and
no,
it
no.
become
This you have to
parallel.
decide. This you have to decide. You'll see the error graph continuously, and then you'll decide, okay, now I want to stop, or okay, no, I want to go further. This is up to your hands. Okay, makes sense, right? I mean, see,
Correct.
what if they can even tell this, that if they can even tell this that how to stop, then I think the problem is done. I mean, then we will be doing nothing, right? We just open and we just say this is the code, read the code and do it itself. Read the problem and do it itself, right? No. The problem is that it will do everything, all the calculations for you, but the mind where to stop the problem, where to go ahead with the problem is still in your hands. You have to still make sure that where do you want to stop the things, or where do you want to again get the further out of it, right? Make sense, right? Okay, let's move forward. I have one more theory for you. Let me paste it. Okay, so don't read this. I'll tell you. This is just for your purpose, so that in the weekdays when you go back and you want to, don't have to like revisit the whole video. Don't review the video. You can just read it through the notebooks only, right? That's why I'm just copy pasting the theory here also. So what happens is, I've already told you that all the edges that you are hit, that you see here, that all these lines that you sorry all these lines that you see here, these are called edges. All the connecting things are called edges. Now for every corresponding edge you have a weightage, right? For every corresponding edge you have a weightage, and these weightages are by default randomly assigned to you, right? Now they're randomly assigned at the very first point. When the problem start at that particular instance, these are like randomly assigned to you. Now for every input in the training data, the ANN is activated, and the and its output is observed. This is what I told you also, right? That once we'll do all the calculations, we'll do the first feed forward neural network, we'll check what the output is, and then the output is compared with the desired output that we already know. And the already know, this is also, you might have heard this term again and again. This is called ground truth, right? So see, deep learning may, you might have heard, this is not equal to what traditional technologies. In traditional programming, you have been given the input and people ask you output. But here it's not like that. Here they will give you the input also and the output also. And then you have to define some way to convert this input into output, right? This is how machine learning works, right? Because they give you input also and then they give you output also. So like say, let's first, on the first example, if someone tells you that you have to do some image classification problem, then this is not like they'll give you at the very first instant, this is the image, now tell me what it is. No, they'll give you a training data set where they will give you the output also. With the image, they will also tell you that, okay, 9 is written here, 5 is written here, 7 is written here, right? So you have the ground truths with you also. Now what you'll do, you'll compare your result with the ground output, and then the error is propagated back to the previous layer. If you read the line propagated previous layer, the error is noted and the weights are adjusted accordingly. This process is repeated till the output error is a predetermined threshold value, or where you think that it is being saturated. Right? This is what I also told you. Now, if I tell you that how it goes, okay, let's see one by one. Mathematically, I'll show you one by one also. Now see, it's pure maths, okay? Just a little attention and then we'll be here. Let's say this thing is called, okay, or otherwise what I can do is I'll just pick up the smaller problem and then I'll show you also how it is done. Okay, just a second. Let me search for the image that I have. Mhm. Okay, sorry, I cannot find it right now. Otherwise, but okay, let's go. Let's see that error is equal to, I'll write it down. Error is equal to, let's say, y actual minus y predicted, right? Let us write down error is equal to this. E, I'll write down. Okay, now if you see that how is this y1 calculated, then let's say that we had an input called, we had an input called I1, and let's say I2, write down, and let's say that we only have this one. Okay, let's make it more simple, right? I will take just this image. That will make you understand how things work, right? Let's copy this. Okay, I'll write it down. Okay, this is the example, right? So now we have input as x1 and x2, right? And we have an output called y. Let's say that the actual or the desired output be ya. right? This is what we require from them. This is how we have, and the value of y is equal to w1 into x1 plus w2 into x2, right? Everybody agrees to this, right? That how is this calculated, right? Now the okay, and let's then define error. Error is equal to y minus y a, right? Or whatever you want to say, y a minus y, doesn't make much problem to us, right? This is how this is working. So now if I say E is equal to y minus y a, then I can say E is equal to, instead of y I can write w1 into x1 plus w2 into x2 minus ya, right? Now if you open up this, doesn't make much sense, but let me write it down. W1 into x1 plus w2 into x2 minus ya, right? Now, sorry. Okay, now the error is this, right? Now, what do you want to do? Now the final equation of error is in front of you, right? If I write it down, the final equation is in front of you. You can now you have the final equation in front of you. Now you have to see that how to minimize this equation, right? How will you minimize this equation? This is the equation of error in front of you. Now what you can do is, now you might be thinking that okay, this error equation is just a simple linear equation, I can solve it linearly. Now imagine that instead of x1 x2 you have 1000 xn, right? Now this equation is not a 2D equation. Now this is a 1000 dimension equation. Now you cannot just simply do things and just check it around, right? You cannot just do it like that. You cannot just plot a graph and you can look into that, right? This is a little more complex than we thought of it, right? If I show you how the graph might look like, right? The graph will look like this. Don't just read this, just for the time being, forget this thing. Just don't read these things, okay? So what I can do is, I say okay, this is your error equation, or let's say error I can also say j of w. You might see this terminology j of w as error, okay? I should not do this. This is not making it good. Okay, when you plot this thing here, now what you can see is, see, x1 is what? X1 is a constant, right? X2 is a constant and y is a constant. You all agree, right? That x1, I will put a star and say x1 comma x2 and ya are constants, right? You cannot change them. These are constants, right? They make no effect to e. The one that might change e is w1 or w2. Okay, for a fact, none of you told me, but we missed a bias also here. Bias b. We missed this bias b here, right? Say this b, but this b is, I mean, it's not going to make some effect to us, but still, just for the courtesy, let's put this, right? To anyone, any doubt is still here, please ask me questions, right? So now we can see that okay, what is happening is that e is only dependent on w's, right? The error is only dependent on w1 and w2 and b. None of the other people are changing this e. So what we'll do is, we'll try to plot this error with respect to the weight, and we'll see this is how the graph looks like. And what do we want to do with the error? If error is ya minus ya, what is our aim? Our aim is to make ya is equal to ya as equal to y, right? This is what our aim is, right? If ya is equal to, then we are saying that the error should be equal to 0, right? Error should be equal to 0 or tending towards 0, right? But if I say mathematically 0 is, if I say statistically, this error is never going to be 0, right? This is never ever tending to 0. So what our main focus is? Our main focus is that if E is here, our main motto is to minimize the current error. Whatever the error is, we have to minimize this error. Now the value of this error can be found here, right? You can simply see the graph and say, okay, this is the value of E. Just take the value of W's and plot them, right? But as I told you, now these errors are not just two inputs. We have like 1,000 inputs, so we might have 1,000 W1s and then one B also. So we cannot just plot it. So it will become a 1,001 dimensional graph. You cannot just plot it. So now we have to think mathematically that how can we minimize the error E. Now minimizing the error E, but we also have the like the equation of E also. We have the equation. Don't think that we have the graph, just think that we have a equation of E also, right? This is above, right? And equation of E is somewhat like this. If I copy this from here, this is somewhat like this, right? This is somewhat like this. This is what the equation of E is, and this is how we have to minimize. Now in mathematics, we have learned, in inferential mathematics, we have learned that if you want to minimize any curve, if you want to minimize any polynomial curve of the order greater than 2, what is the process? Can anybody tell me? If you want to find out, if you want to know that where is,
First
yeah,
derivative, I believe.
I'm sorry, what?
Take the first derivative
Take
of
the
that
first
curve.
derivative. Okay,
Yep.
okay, correct. Take the first derivative. That's very much correct. So as Omar said, that you have to take. So see what the first derivative tells you. The first derivative tells you that wherever there is a change in the slope of the graph. If I talk about what we learned in our higher education about differentiation, was that differentiation tells you that point coordinate where the graph changes its slope from positive to negative or negative to positive. So if you take the first derivative, it will tell you this place. See, it was in negative slope, then it came in positive slope. Now again here, when it was in positive slope, then it came into negative slope. Again positive, negative, positive, negative, positive, negative, positive, negative. So it will tell you all the places where it has uh, changed the slope from positive to negative or negative to positive. Vice versa, it's possible, right?
Yeah, but
Sorry.
like for global minimum and maximum, you have to take the second derivative instead of
Second
using it.
derivative. Correct. So this was how we talk about inferential mathematics. But if you go in descriptive mathematics, it says that what is a derivative of a function? A derivative of a function when you have a tangent that is parallel to the x-axis, right? When it is parallel to the x-axis. So how where will be the tangent parallel to x-axis? Whenever there is a slope that is equal to 0. So if the slope was from positive to going to negative or negative to positive. So both the mathematical percepts tells you that there is a change in the slope in that, right? So similarly, we can know that where are the positions, where are the places where we can get a change in the slope. Now, as Omar very he suggested that we will get all the points where it is maximum and minimum also, and we just want the point where it is minimum. I mean these points, we are interested in the one that are by dotted by green, either this, either this, either this, right? But now again there's a problem is that these are very higher error. This one that I'm just marked as E1, this is a very higher level of error, right? We don't want a higher level of error, we want a lower level. This one we want the E3. We want E3 to be our error. So what we do, we take double differentiation. We first take differentiation, then we take double differentiation. Now double differentiation, then Omar, can you tell me what is the condition? If it is less than equal to or equal to less than 2? Okay, I'll tell. Now, with the first derivative, you can know that where is the slope of change. But if you want to know that what it is, if it is a maxima or if it is a minima, how do you know it? You know by doing a double differentiation of that thing and then checking its dimension. So if the double derivative of any of your function is greater than zero, if the double derivation of a function is greater than zero, then it is a minima, right? And if the double derivation of any of your function is less than zero, then that is maxima. These are the conditions. Then you will check accordingly and you will go for minima. Now again the problem is that okay, now you will reject these points. You will reject all. Okay, so you might discard this, you might discard this, you might discard this, you might also discard this, right? So you will remove all these blue points. Now you will only have the green points with you, right? Now you want this E3 to be there, right? Now we don't have any mechanism through which we know that we have reached global minima or not. This is the dilemma in deep learning. And so slowly what we do is now understand this mechanism. This is called this whole thing that I'm showing you right now is called gradient descent or GD, right? You might have also heard this as SGD, stochastic gradient descent. When you do a gradient descent in batches, it is called stochastic gradient descent. Okay, I'll take a pause here, and to anyone who has not understood this thing, please ask. I know I might have taken a very quickly this up, and again one more point to other people also who are not math heavy. See, this maths is just for your understanding. You won't be doing all this maths in your programming. No, you won't be doing all this in your deep learning courses. You will be just writing the direct code. You won't be doing all this mathematics. This is already done by the framework, so don't worry about this. But again, my point is, please try to get this inside, because this is necessary, right? This is necessary. If you don't understand what is your framework doing, then there is no sense of your framework doing something, right? So uh, so just please, and if you have any doubts, please ask, do not hesitate, because I know it took me 3 days to understand this thing. So I was how do you put, okay, so I am assuming that everybody understands still here. Okay, so what I'll do is I'll take the first derivative of dE, sorry, dE. Now you know that E is equal to this. Let's write it down. So now you have seen this one thing, that the E is dependent on either W1 or W2. So what you'll do is you'll take the derivative with respect to one time with respect to dW1. So what will happen? It will say x1 and then everything is equal to 0, right? Because these are all constants. Am I correct or wrong? What I'm doing is I'm trying to take a derivative with respect to W1. What will happen? X1, correct. X1 into 1, totally correct. Plus W2 is again a constant, plus constant plus constant. Makes no sense, right? That's there. And if you want dE by dW2, then what will happen? It will give you X2, right? X2 into 1. Don't worry again to, okay, it's in chat. Just a second. Again, see, someone is asking me this question that is this really required? No, this is not required. This is just for your reference. Don't worry.
Shivam, I think
Okay.
you need to add a constant term too into the derivative.
Oh yes, yes, yes. So we need we add a constant term, but here we know that constant term is equal to 0. So yes, he's right. We'll have some C1, C2, but these are constant as of now for us. They don't bring much value to us. I'll put this picture around. So see, this was just for one, right? If you go from here till here, this was just for adjusting the new values. Now what will be the adjusting values of W1 and W2? So now we already have the older values of W1, W2. So the new value of W1, W2 will be dw is equal to W1 minus dE by dW1, and W2 will be equal to W2 minus dE by dW2, right? This will be equal to this, and but there is a special term that is called alpha that is associated here. It is multiplied here. I'll tell you what alpha is here. I don't know how to type alpha in like latex, but okay. Okay. So now you might ask that okay, now we understand that this is the new value of W1 and W2, right? So now what will happen? This older value of W1 and W2 will be replaced by the new one, and then you again go forward, and then you again get the error, again come back, change the value, again go forward, backward, forward, backward. But there is one thing that you might ask me, that what is this A here? This A is called alpha. Sorry, this is not A, this is actually alpha, and this is also called as learning rate, or you might see people calling as LR. Right, now what learning rate is, now just pay a little attention towards here, right? So let's say the previous value of W1 and W2 will give you some error that would be here at this point, the one that I draw very small here, right? The next one will be here, then here, then here. So it might vary that how gradually you are moving your W. Let's say that you are making very small change in W, very small change in W. So your error, let's okay. Let me maximize it. Okay. So now let's say you have taken some initial value of W such that W1 such that the error is here, right, at this point, at this particular point. Now you make a very small change in your W1 and make it to W1 dash. So what will happen? The error will shift very slowly also, right? Your error is also going to shift very, very slowly because you have made a very small change in W1. Or otherwise, let's assume that you might, there your W1 originally was here and you made a very big change in W. So your error might be here at this point, new error might be here, or it might also happen that it might come here also, right? It might change that how gradually you're moving your W. So there is this terminology that says that you should very slowly move your W so that you don't miss your minima. Assume again, let's assume that you slowly moved your hair till here. So you have come till here, your W1 is here now, and now you suddenly increase, you did a change in W1 so large that you came here, you came at this point. Now this is bad because you missed the global minima in here, right? So what people say that you should very slowly move the value of W, very slowly. You should do all the changes very slowly, and your dE by dW, your dE by dW should be controlled by some another external factor, and that factor is called alpha. Now because if you go down the screen, if you see, I have multiplied this dE by dW term with a thing called alpha. Now this alpha is with you. This is a constant and this is in your hands. You can change it anytime that you want, right? So what you will do is, I'll move back up here. So what you will do is that you will select the value of alpha such that it is moving very slowly, right? But now there's a disadvantage also, because if you move very slowly, then let's say you are here, then you will come here at this point, then here, then here, then here. So you might reach your global minima at a very, very larger time. It will take a lot of time to you. So you have to take a very critical value of alpha such that it moves very slowly. I mean, not
So
slowly, but yeah.
are you trying to like tune up your model?
This is not tuning, it is just adjusting the thing, that how the model is reacting to the changes that we are doing. So it's like we are controlling our own process of the flow of gradients. And alpha, keeping the value of alpha, yes, you can say this is one of the parameters of hyperparameter tuning. Hyperparameter tuning, HPT. Yes, this is one of the small features that you are tuning. So the value of alpha you should keep is 0.001. But again, if someone says you this, well, like I just said you that you should keep your alpha, no, I'm totally wrong. It depends on your data, that how slowly you see that your model is moving. This is just the initial value that you should take. So if you will see all of your major frameworks like Keras or like TensorFlow, you will see that they have put a value of 0.001 also by default. Make sense?
Just a quick info, guys. If you want to become a certified AI professional, then check out the Artificial Intelligence course offered by Intellipaat. You can find the link in the description box below. So this brings us to the end of this session. If you have any queries, please do put your comments in the comment box below and we'll reach out to you immediately. Also, do subscribe to our channel to stay updated about our upcoming videos. Thank you for watching this video.